Every year, the world produces over 20 billion pens, enough to give every person on Earth more than two each. From classrooms and offices to factories and airports, this small tool quietly powers global communication. But behind its simple appearance lies an industry built on chemistry, precision molding, and non-stop mass production running day and night. Despite how ordinary a pen seems, manufacturing one requires an extremely precise sequence. Molten plastic must be shaped within milliseconds. Ink formulas must be filtered at microscopic levels. Ballpoint tips must be machined with tolerances smaller than the width of a human hair. One wrong temperature, one clogged nozzle, and tens of thousands of pens can be instantly ruined. How does crude oil become the transparent barrel you click every day? Who manufactures the tiny metal ball that glides across paper? And what kind of machinery can assemble more than 1,000 pens per minute with near-perfect consistency? The pen's design looks simple, but the engineering hidden inside it is anything but. Today, we'll step inside high-speed production lines where plastic pellets, metal alloys, and chemical dyes transform into one of the world's most essential writing tools. You'll see how ink is engineered, how ballpoint tips are carved, and how automated robots assemble millions of components with quiet precision. This is how the pen, a tool found on every desk, in every bag, in every school, is made through a global process few ever witness. This is how it's created, from start to finish. Long before plastic barrels and ballpoint tips, writing began with reeds dipped in ink and sharpened feathers guided across parchment. For thousands of years, these tools shaped stories, laws, and history itself. But human progress demanded something faster, a writing instrument that was portable, durable, and ready the moment it touched a page. The breakthrough came in the early 20th century with the invention of the ballpoint pen. Its tiny rotating ball trapped ink inside the barrel and released it smoothly onto paper, solving the age-old problem of leaking bottles, fragile nibs, and constant refilling. What began as a luxury accessory quickly evolved into the world's most accessible communication tool. Today, pens exist in staggering numbers. More than 20 billion are produced each year, from ballpoints and gel pens to rollerballs and technical markers. Factories across Asia, Europe, and the Americas run around the clock to meet global demand. Students use them to learn. Offices rely on them for signatures and documents. Hospitals depend on them in charts and records. Even in the digital age, the pen remains irreplaceable. Behind this massive industry lies a global network of materials and technology. Plastic is sourced from petrochemical plants. Metals come from refineries, ink ingredients are extracted, filtered, and blended in dedicated chemical facilities. From these raw components emerges an object so common that most people never question how it's made, or how many hands and machines shape it before it reaches their desk. To understand how billions of pens come to life each year, we must first follow the journey of their most fundamental material, the plastics and polymers that form the barrel, cap, and interior components. This is where the true industrial story begins. Every pen begins its story deep beneath the earth, where crude oil is drawn from ancient reservoirs and transported to massive refineries. Here, under intense heat and pressure, hydrocarbons separate into the building blocks of modern materials. One of these fractions, naphtha, becomes the foundation of nearly every plastic pen body in the world. Naphtha is sent into towering steam crackers, where it's exposed to temperatures reaching 800 degrees Celsius. In these extreme conditions, its long hydrocarbon chains break apart into simpler molecules such as ethylene and propylene. These gases are the essential ingredients for creating polypropylene, the primary plastic used in pen barrels and caps. Inside sprawling polymerization reactors, ethylene and propylene molecules snap together into long repeating chains. The result is tiny translucent pellets, smooth, uniform, and surprisingly lightweight. Each pellet contains thousands of linked molecular units, giving it strength, clarity, and flexibility once formed into a pen. The pellets are mixed with color pigments, UV stabilizers, and impact modifiers. This blend ensures that every pen barrel remains durable, bright, and resistant to cracking. Whether it's dropped in a classroom or clipped to a pocket thousands of times once prepared, the mixture is loaded into sealed containers and shipped to pen factories across the world. When the pellets arrive on the production floor, they no longer look like the origins of a writing tool, but hidden inside them is decades of chemistry and engineering refinement. Under the right temperature and pressure, these tiny beads will become the smooth, rigid, perfectly shaped barrels we hold every day without a second thought. And that transformation begins the moment they enter the molding machines, where heat, pressure, and precision shape molten plastic into the familiar form of a pen. Inside the molding hall, the world of plastic transformation comes alive. Conveyor belts hum softly, robotic arms glide with clockwork consistency, and steel machines open and close like mechanical lungs. This is where raw pellets become the physical body of the pen. The polypropylene blend is poured into large hoppers, then fed into heated barrels, where temperatures reach nearly 250 degrees Celsius. Inside, rotating screws crush, mix, and melt the pellets into a smooth, molten stream. In seconds, the plastic becomes fluid enough to take any shape engineered by the molds waiting below. At the heart of the process are multi-cavity steel molds, carved with microscopic precision. Each cavity represents a pen barrel, a cap, or an internal component, reproduced dozens of times in a single mold under pressures reaching thousands of psi. Molten plastic is injected into these cavities, filling every contour instantly. Cooling channels circulate chilled water through the mold, solidifying each part almost immediately. When the mold opens, robotic extractors lift out a full set of perfectly formed components, still warm, still glowing faintly from the heat that shaped them. The barrels roll onto inspection conveyors where excess plastic is trimmed away. Caps are molded separately, often using softer polymer blends for flexibility. Click mechanisms, inner tubes, and grip sections are produced in parallel lines, each one molded with tolerances measured in fractions of a millimeter. If even a tiny dimension is off, the clicking mechanism may jam or the ink tube may fail to fit. For more advanced pens, two-shot molding combines rigid and soft plastics in a single piece. Grip sections with rubberized textures and colored accents are injected directly onto the barrel, fusing permanently without glue. This creates the comfort and ergonomic feel many pens are known for. By the time this stage ends, thousands of barrels, caps, and inserts flow out of the machines every hour, uniform, precise, and ready for the part that truly defines a pen, the ink and the ballpoint tip that bring words to life. Before any pen can write a single word, its most important ingredient must be perfected: the ink. Hidden behind factory walls, far from the molding machines, are controlled mixing rooms that look more like chemistry labs than industrial floors. Here, technicians engineer the liquid that will travel through a metal ball, smaller than a grain of sand, and leave a smooth, consistent line on paper. Ink begins with a base of refined solvents or water, depending on the type of pen. Ballpoint ink uses thicker, oil-based formulas engineered to dry quickly. Gel and rollerball inks rely on water-based solutions mixed with gelling agents to achieve their signature smooth glide. Each formula must strike the perfect balance between viscosity, flow, and drying speed. Too thick, and the pen won't write. Too thin, and it will leak. Pigments and dyes are added next, measured with digital precision. The slightest imbalance can shift color or affect opacity. High-speed mixers churn the blend for hours, breaking down every particle until the ink becomes perfectly smooth. Advanced filters remove impurities at the micron level, so fine that even a speck of dust could clog the narrow metal tip of the pen. Once the mixture reaches the exact thickness required, samples are tested on automated writing machines. These devices simulate human handwriting at different pressures and speeds. Each stroke must remain even, bold, and uninterrupted. If the ink leaves gaps or blobs, the batch is corrected or discarded. When the formula is approved, the ink is pumped into large stainless steel tanks connected to filling stations. Transparent tubes carry the liquid into thousands of tiny ink reservoirs that will soon sit inside the pen barrel. Each reservoir is filled with a precision nozzle that injects just enough ink for weeks or months of writing, depending on the pen's design. Some factories add a safety feature, a small plug of absorbent material at the base of the ink tube. This prevents leaking during air travel or sudden temperature changes. Others seal the tip with a protective wax droplet that melts away during the first use. By the time this stage ends, the most critical component of the pen, the engineered ink, is ready. Now it must meet the only part capable of delivering it to the page, the tiny, perfectly machined metal ball that turns liquid science into written language. If the ink gives a pen its voice, the ballpoint tip gives it the ability to speak, and crafting this tiny metal part, barely a few millimeters long, is one of the most demanding precision engineering tasks in the entire manufacturing world. The process begins with thin rods of brass or stainless steel, chosen for their corrosion resistance and ability to withstand constant friction. These rods are fed into high-precision cutting machines that slice them into tiny cylinders, each one destined to become the housing for a microscopic metal ball. Next, CNC microdrills carve the internal channel that will guide ink toward the writing point. The tolerances here are extraordinary, often measured in microns. Smaller than the width of a human hair, a channel too narrow will choke the ink flow. Too wide, and the pen will leak or blot. Every detail must be exact. Then comes the defining step, the seat for the ball. A diamond-tipped tool forms a perfectly rounded socket at the tip of the metal housing. This socket must hold the ball firmly, but allow it to rotate freely in every direction. Even a microscopic defect could scratch paper, jam during writing, or cause the ink to smear. The balls themselves are engineered separately, usually from tungsten carbide, one of the hardest materials ever created. Each tiny sphere is polished in vibrating ceramic basins until it becomes flawlessly smooth. A single ballpoint pen relies on this perfect geometry to transfer ink evenly across thousands of strokes. Once both components are ready, automated assembly machines press the ball into the socket with incredible precision. The fit is so precise that no glue or welding is required. The ball remains trapped, yet spins effortlessly. A perfect marriage of pressure, geometry, and engineering. After assembly, every tip undergoes strict testing. High-speed optical systems inspect the ball's rotation, the alignment of the socket, and the consistency of ink flow. Any imperfection sends the tip back for recycling long before it ever reaches a pen. By the time these metal tips roll out of the production line, they have passed through one of the most demanding micro-manufacturing processes in the world. Each one is ready to be joined with its ink reservoir and molded barrel, ready to become the writing tool billions of people rely on every day. With barrels molded, ink prepared, and ballpoint tips engineered to microscopic perfection, the final stage of the pen's creation begins. This is where thousands of individual components merge into a single tool, fast, fluid, and flawlessly consistent. Along high-speed assembly lines, robotic arms pick up empty barrels and place them into synchronized clamps. Ink reservoirs glide toward them on parallel conveyors, each tube filled with just the right amount of engineered ink. Precision nozzles insert the reservoirs into the barrels with a gentle, controlled push, ensuring a perfect fit without stress or bending. Next comes the heart of the process, the union of the ink tube and the ballpoint tip. Automated drivers press the metal tip into the open end of the reservoir, sealing the ink inside. The connection must be airtight. If even a tiny gap exists, air bubbles can form, breaking the flow of ink during writing. Only perfect seals continue down the line. Caps, clips, grips, and click mechanisms are added in rapid succession. Click pens receive their signature spring-loaded action through compact assemblies snapped into place with robotic precision. Stick pens receive their simple, friction-fit caps, molded moments before multicolor pens are fitted with rotating cartridges that allow different inks to snap into position with the turn of a selector. Once assembled, every pen enters a testing stage. Automated writing machines press the tip against rolling sheets of paper, drawing continuous lines to ensure ink flows smoothly and consistently. Sensors monitor color density, line weight, and the absence of skips or blotting. Any pen that fails is pulled instantly, its components recycled into new material. The pens that pass move to sterilization and cleaning tunnels. Soft jets of filtered air remove dust and microparticles. Some factories use UV chambers to ensure hygienic handling before packaging. Finally, packaging machines arrange pens into blister packs, boxes, or bulk trays. Clear windows showcase the colors. Printed labels include batch numbers, production dates, and barcodes for global distribution. Sealed cartons stack onto pallets headed for shipping hubs around the world. In days or weeks, these pens will travel by truck, ship, or air cargo to supermarkets, schools, offices, and homes. A tiny object molded from molten plastic and engineered metal will soon sit in someone's pocket, ready to sign a form, write a note, or begin a story. From raw pellets to ink strokes, the journey is now complete. Yet its impact begins the moment it touches paper. From the heat of petrochemical reactors to the quiet precision of micro-machined metalwork, the pen's journey shows how industrial innovation transforms the simplest ideas into global necessities. What begins as crude oil deep beneath the earth becomes a tool capable of capturing thoughts, recording history, and shaping human communication. Every barrel, every ink reservoir, every polished tungsten ball represents a chain of engineering decisions made with one purpose: reliability. A pen must work instantly, consistently, and without fail. Whether it's signing a contract, filling a notebook, or helping a child learn to write their name for the very first time. It is easy to overlook something so small, yet billions of them circulate through our hands every year. They travel across continents, pass through classrooms and workplaces, and become extensions of our ideas. In a world dominated by digital devices, the pen remains timeless, a reminder that the simplest tools often have the most enduring impact. Behind each stroke is an entire world of chemistry, machinery, precision, and human ingenuity. A world few ever see, yet one that powers daily life in ways we rarely stop to consider. This is how the pen is made, from start to finish.